Good morning, good day, good afternoon to all of you to this webinar on the continuing topic of process control using LVProSim. So once again, we will be using this simulator to show you how you can teach process control for your students while you're at home and they are at home. Again, I am with my colleague Gonzalo, who will be helping me out today answering your questions. Good morning, Gonzalo.
Hello, good morning, Christian. A pleasure to meet you again after the long weekend.
After the long weekend, yes. So I don't know where you're listening us from, but yesterday was the first real day of summer in Canada. So everybody was outside working in their yard. That was really a great day. So that's why Gonzalo and I are a bit more suntan than we were last week. So we are expecting about 40 people this morning, only half of which are currently online. So I will just start by well, once again, yeah, just if it's your first time participating to one of our webinars, I would like you to raise your hand. So you will see a little button with a hand icon on it. So if you could just raise your hand, click on this button if it's your first time attending one of our webinars. Good, so we have 2 new people. Okay, so hopefully for these people, you won't be too lost in the topic, because this is the first time we really do a webinar that is a continuation on a previous one that was started last week. If you're familiar with the concept of process control, it won't be difficult to follow us because what we just did in the last webinar was covering the basics of process control, finding the characteristic of a process. That's what we did. So today we will start tuning our feedback loops, our loops by our PID loops by playing with the P, I, and D parameters, as we will see. So I think that we will start now, or have about, yeah, half of the people are online. So let's start with the webinar itself, the topic itself, which is process control. Again, second part. So what will be the topic of today? Well, PID process control. So this covers lots of stuff. I will try to be short on the theory so we have more time to play with our simulator. But still, for you to understand what we are doing with the simulator, some stuff needs to be covered if you're not as familiar with the topic. So first we will look at what is feedback control. Then we will start with the simplest of all types of controls, on-off control. Then PID control, which is proportional. So instead of being just on-off, it will be the answer of the system, the response of the system will be proportional to the error. Then we will look at from PID in progressive order. First, just proportional control. Then we will add the integral parameter, then add the derivative parameter, and finally have a quick look at the proportional and derivative controller, which is really rarely used. We will do a comparison of these 3 types of controls and look at the structure of a different structure of controllers. So first, we need to define what is reverse and direct action. So simply, it's that the answer, the response of the controller will either change in the same direction as the error or in the opposite direction. So if we are set in direct action, the controller output increases when the controlled variable increases, while in reverse action, the output will decrease or increase while the variable decreases, or vice versa. So we have 2 examples here to understand why this distinction is essential. It depends on the types of final control element basically you have, as we can see here. So here we have a fail close valve, which is the output of our tank here. So a fail close valve means that if it does not receive any signal, meaning that maybe the cable is cut, so we are in a fail mode. So if it does not receive any signal, the valve will close, totally close. So fail close. Such a valve is fully open when it receives full signal, 100%, and fully closed when it receives 0. While a fail open valve is just the opposite. When it receives no signal, it is fully open. So you understand that the controller that is here on the fail close size, when it wants to close the valve, it needs to send a 0 signal, while this one needs to send 100% signal when it wants to close it. So of course, the action of the controller will be completely opposite in these two cases from the same scenarios. So to receive the same to achieve the same result on the level, it will need to send an opposite signal to this valve and this valve, depending because of the nature of the valve. So direct or reverse action. Then distinction, the first type of control, on-off control. So on-off control is simply, as it says, really simple. The controller will always send either a on signal or off signal, or if you want, it will send to the manipulated variable. It will send either fully, let's say, for example, it's a pump. Okay, so it will send to the pump 0 voltage, so the pump will be completely off, or it will have the pump turn at full speed. Okay, so either the pump is off or the pump is at full speed. So of course, this type of control is typically we will not use that with a pump. It will be used for a process where we have a large capacity that really changes slowly, as you can see here, on large capacitance, slowly changing processes. So typically we will find that in heating processes. For example, in the oven, that's exactly in a kitchen oven, that's exactly what happens. We just either send full current to the heating elements to heat up the oven, or we just shut them off and then the oven cools down. As we can see here, the oven will constantly either increase its temperature, then we shut off the heating element, the temperature will go down until we reach a certain point, at which time the controller will send another on signal to turn back on the temperature, the heating inside the oven. Same thing for house heating. We just turn on, full on or full off the heating elements in the house to keep the temperature constant. So the temperature basically constantly oscillates between a upper value and lower value. So these are on-off controllers. On-off control, we won't do an example of that today. We will want to concentrate really on proportional PID control, which is presented here. But before I dive into PID, any questions, Gonzalo? Hello? Oh, we lost Gonzalo, I think.
Yes, no questions.
No.
I was answering a question, so everything is doing right. You
Perfect.
can keep going.
Thank you, thank you. Okay, so we can see here the mathematical aspect of PID control. So don't be scared. We will look at it in a more human way, but mathematically, this is what it gives. So basically, when we are talking about proportional, integral, and derivative control of a loop, we are referring to the way that we will respond to a change in the error in our system. So first of all, what is the error? The error is always the difference between the current value of the parameters we are controlling and the desired value. So let's say that I want to be at 50% level in my water tank, and currently the water level is at 40%, then 50 minus 40, my error is of 10%. So of course you will understand that a controller should not respond the same way to an error of 10% than it will respond to an error of 50%. So the response should be much more aggressive if the error is larger. So that's what we mean when we speak about the error. Well, we will see that there are different ways of producing a controller output signal from the error. The first one is proportional. So proportional will simply multiply the error by a fixed gain, okay, which is the controller gain to produce an output, which is here M stands for manipulated variable. So our manipulated variable, let's say the speed of the pump, for example, will be equal to the current error multiplied by a constant parameter, by the controller gain. And then we add to that, of course, a bias, because oftentimes, even if we have no error in our system, we need to have our manipulated variable not at 0. So for example, to maintain the level at the current level, we need to have the pump to spin maybe at 20% just to keep the level constant, because there is water coming out of the tank constantly. So by spinning our pump at 20%, we compensate this outflow, and this is our bias in this case, okay, the B here. So this is the proportional term. Integral term is where we will basically, well, I'll discuss about it later, but basically we will correct long-standing errors with the integral parameter, and finally the derivative parameter, taking the variation speed of the error. So at what speed does the error change? We will add a term responding to the speed of change of the error, which will yield the derivative parameter. But we'll come back to it in a moment. All of these parameters are set together inside the control equation, basically, as we can see here. So the manipulated variable, let's say once again, our pump speed, will be equal to the sum of all these parameters if we are in PID control. So P here, I here, and D here. And you can see in this equation here that our controller gain is right here at the start of the whole equation, and multiplies each of these terms. So each term is multiplied by the controller gain. The bias is, as I was telling you, the value that we have to send out of our controller when the error is 0. So we have the error here, and as you can see, as the error increases, the response of our controller will increase also. So let's first have a look at the proportional controller, the simplest of controllers, where we, and this here, what you see, the schematic at the bottom here, is really what we all see all the time in feedback control. So basically we have our the output of our controller here after the KC box. This is the output of the controller, which feeds the pump, for example. But this signal is fed back to here. The measurement from the transmitter, for example, sorry, what I said, this is not the output to the pump. This is the output of our process, which is the parameter we are controlling, for example, the water level. So the water level will be measured, sent back here, compared to the set point. This will yield an error. So basically they will be subtracted from one another. And then the error will be multiplied by KC, our controller gain, to provide us with a proportional response to the error. So this is a proportional controller. So as you can see, as the gain increase. So here we have different gains for the same situation. Okay, we just have just increased the gain between all these curves. That's the only difference. So with a gain of 0.3, we are down here. Gain of 1, 2, 4, 10, and 20. So as you can see, as the gain increases, the response of the controller, because this is the controlled variable here, the response will be much steeper, much more rapid. So initially, slow response, faster response, faster. And then at this point where KC equal 4 here, we start to overshoot because we take for granted here that we are trying to achieve 40%, okay, for example. So we overshoot the value and then come back to the value. And if we increase the gain again, we will overshoot even more and start oscillating in our response. And eventually we might even reach a point where our gain is so high that the response will become really oscillatory and will not stop oscillating. Okay, then we say that we are in constant oscillation, and that's definitely something we want to avoid in a process that we are controlling. So for example, let's say that we would like to maintain the tank level to 50%, and instead of having that, we would have our tank levels constantly fluctuating between 40% and 60%, 40, 60, 40, 60, with the pump kicking really hard, to keep this running. So this is the kind of response we do not want to have. So we will have to find the proper value of the gain to give us the type of response we want. Depending on the process, what might be most important is the speed of the response. In some other processes, it might be that we never want to overshoot, that it can be slow, but we want it to be always in controlled mode and really close to the value, never overshooting. So depending on the process we are controlling, we will have to select the proper gain. So here we see what the three parameters that are constantly monitored in a process: the set point. So when we do a set point change, how will the manipulated variable respond to that? For example, our pump speed. So the pump speed, of course, will increase to increase the level in our tank to reach the new set point. Okay, and then when the controller will realize that the level is increasing too much, it will slow down the pump because it doesn't want to overshoot the new set point. But then the level will start decreasing, so the controller will respond to that by increasing again the pump speed to eventually reach the proper value. As you can see in this schematic here, it's not a mistake where we have our controlled variable not reaching exactly the set point, okay? So we can see here that even after we have reached a new stable state, our controlled variable is not exactly at the set point. This is exactly the problem with P control. So when we have only proportional control, we can set the gain, to achieve a faster or slower response, no problem. But we will never be able to get rid completely of the fixed error that will remain there. There will always be an error that will stay between the set point and the controlled variable. And we will see that that's why we normally use the I parameter also to prevent that. So why is this error remaining there? It's simply because at some point the error becomes so small that the controller is not able to respond to this error either because of the sensitivity of the sensors or because of the signal, the fineness of the control we have on our final control element, the pump, for example. Okay, so the error we get might be so small that it will produce a really small difference voltage output at the difference of our controller, which will make no difference on the pump speed, for example. So if the output of the controller is so small that the pump does not respond to it, well, the variation, the error will remain there because there's no way for us to control more precisely the pump. That's an example. So that's what we will try to fix by the I parameter, as we will see later on. So the controller gain here determines the magnitude of the proportional action. Sometimes it is defined as the proportional band because some manufacturers of controllers have different terms. So it's either the controller gain or the proportional band. They are just the opposite of one another, mathematical opposite. Be careful not to confuse the controller gain with the process gain. So yes, last week in our first webinar, we discussed the process gain. We found that the process gain was the variation of the output divided by the variation, the ratio of the variation of output on the variation of input. Here, the controller gain is really the parameter by which we will multiply the error to get a controller output. Whoops. So we say here we introduce the integral term. So now that we have discussed the proportional term, the integral term is there to eliminate the offset left by the proportional term, just like I was telling you. So it will eliminate this offset here between the set point and the control variable. How will it achieve that? Well, it will achieve that by, as its name implies, integrating the error. So for those of you who are mathematically savvy, you will know that the integral is basically the sum finding the area under a curve. Okay, so if we have an error like this here, okay, integrating the error means calculating the area under this portion of the curve here. Okay, so if I calculate this, if I add up the sum of the, so at this point in time, okay, I will have this little area under my curve, which will yield a small increase here in my integral parameter. But as the time goes by, as you can see, the area under the curve becomes larger and larger, which means that the response of my controller becomes also larger and larger. Of course, the opposite is true. If we have a negative error, then it will decrease. So the area will be smaller, will be negative, and it will decrease the output of our output. And if we have no error, because the value is exactly at, well, our error, as you can see here, is 0, then the output of the integral parameter will stay stable, will stay at the same value, at a fixed value, because there is no area anymore under the curve. So why do we do that? Well, basically the not why we do it to correct the error, but the mode of action, as you can see, is that the longer the error is there, the higher the controller will send the stronger the signal the controller will send to correct this error. So that's how eventually we will fix the error that was there. So the controller will increase the output here to increase the speed of the pump to eventually have our level reach the set point. And then if ever the level was going above the set point, then the error would become negative, in which case the output of the controller will start decreasing to get closer to the set point. But because of the integrative nature, we are sure that the error will be corrected because it will look in the past. Basically, the controller looks, okay, what was the error? What was the level of the error in the past few seconds? And it will correct based on the information of how the error evolved over the past. So that's how it will correct it. When the integral parameter can be defined either as the repeats per second, or the reset rate, or the time, the integral time. Okay, so the integral time constant. So again, it's the reciprocal. The integral time is the opposite, the reciprocal of reset rate. And again, it's just a distinction of definition and how the manufacturer of the controller wants to define that. In our case, in our examples, we will be using the integral time, but know that you might meet the reset rate at some point. So here is our full equation, as we already saw, again with our controller gain distributed to all terms here, and then our integral term with TI and our derivative term with TD. Be aware that TI here appears at the denominator, so it will act in an opposite direction as a KC, the controller gain, and TD, the derivative term, which means that KC and TD, the bigger they are, the more impact they have on the output of the controller. For TI, it's the opposite. The bigger it is, the lower the impact of the integral parameter. So we will need, in fact, to decrease the value of TI if we want to have a higher integral, stronger integral response to our equation. And here we have a graphical comparison of the different response we will get from the different type of controls. So with no control, as we saw in the last webinar, if we do a change to a, well, in fact, it's not even a change to the set point, it's a change to the output variable that we would get of the input variable, we will get an output. So we're not concerned here. So let's look here with our PI and PID. So with a P parameter here, P control, as you can see, we will respond quickly, more or less, with small oscillation, but we will always maintain the small error we were discussing. Then if we add the I parameter, which is the red curve, okay, then as you can see, we will have a stronger and faster response when there is an error to an error. It might oscillate a little bit more depending on how we have set our parameters, but as we can see, eventually it will reach a new stable state and we will be right on the set point with no offset. And finally, if we add the D parameter, which is PID here, the black curve, you will see that we will reach if we are properly set, we will reach a finer control with less overshoot. As you can see here, less overshoot, less oscillation, and so it will stay closer to the set point and it will reach the new set point faster. So it depends on the process, but if it's a process that is adapted to PID control, if your PI and D parameters are properly set, this is the best control you can have, basically. But some process does not lend themselves to D control because D can insert lots of instability in the system also if it's used on a system that is not meant to be controlled by a D parameter, as we will see. Structure of controllers, and then we will dive into our exercises. So the first type of controller that we'll look at here is what we call non-interacting controller. What does it mean, non-interacting? It's simply that, as you can see, the way that the controller calculates the parameters, each parameter is independent of the other. So if we do a change to the integral parameter here, it will have no impact on the output of the D parameter and vice versa. So that's why we call it non-interacting. And typically, this is not what we find. This is not what we find in the industry. Okay, the reason we use that, and this is what we use in our LVProSim software, a non-interacting controller. The reason we use it, and typically the reason it's used, is for teaching purposes, because it's much easier for the students to understand the impact of each parameter if they are processed separately like this, because they can play with just the TI parameter and see the impact on the output of just this parameter instead of having it impact the whole the other terms. The problem with that is that it leads to a less stable control, so it's not as easy to achieve control with a non-interacting controller as it is with an interacting controller that we find in the industry. So the mathematical equivalent of this is what you see here, where you have each parameter that is separate from one another, and all of them being multiplied by the controller gain. The interacting controller has the equation like this here, where, as you can see, the integral parameter will be multiplied by the derivative parameter. And same thing for the proportional parameter also. So all parameters are interacting with one another. That's where the term comes from. And the graphical equivalent of that is this here, as you can see. So KC will have an impact on TI, which will have an impact on TD, which will have an impact on the whole thing. So it's basically all multiplied with one another. We achieve better control, easier, more stable with that, but less easy to understand. So that's why it's not used in this course. And finally, the parallel controller is this term here. Sorry. That where the only difference with the non-interacting parameter, as you can see here, is the fact that KC, our controller gain, is not multiplying the other two parameters. It's treated separately here. So as you can see, KC is not multiplying the other terms here. Okay, so we reach our exercise. We're done with the theory. So how is it going, Gonzalo? Any questions?
No, not question right now. We're okay. Just administrative questions, we're fine.
Perfect, thank you. So let's find now that we understand a little bit more about the mathematics and the different parameters of a process control loop, how to find the proper values for these P, I, and D parameters to achieve proper control in the loop. So the first way to achieve it, and that's the one we will try now, is the trial and error method simply. So we will we will first start with the P parameter, set it to find a proper value for it. Then by changing its value, seeing how the system responds, if it's not responding strong enough, we will increase the value. Eventually, we will reach a point where the P parameter is responding too much, so we will come back to a previous value of P. Then we will do the same thing for I, and then the same thing for D, and eventually we will have found the 3 values that yield a good result. So there's a little block diagram here that we can use to help us in finding the proper value. So with the controller in manual mode, turn off the integral and derivative actions, set the controller gain to 1. So we start with a gain, which is KC, a value of 1. We place the controller in automatic mode. We make a step change to the set point. If the response is underdamped, is the response underdamped and oscillatory? No. We increase the controller gain to twice its value. So each time, each step, we will double the value. So we will increase the value to 2, and then make a step change. See if it's underdamped. Is it oscillatory? No. We double again 4, and then if it becomes oscillatory, yes. Then we will set the gain halfway between the actual and the previous gain. So if at 2, at a value of 2, it was not oscillatory, and at a value of 4, it becomes oscillatory, then we will simply set the gain to 3. Okay, and this will be the value for our gain. And then we will do the same thing with the I parameter, and then the same thing with the D parameter. Except that, of course, with I, instead of starting with a low value and multiplying by 2, we will start with a high value and divide by 2 until we reach the proper control. And for D, we will do the same thing as with the gain, starting with a low value and multiplying it. But in this case, in the case of the derivative parameter, when we say a low value, it's really a low value, like 0.1 or something like that, because the derivative action usually have quite a huge impact on the response. And here we have graphically help, a schematic that provides lots of help in determining what we should do. So here in the center, as you can see, is the response we get for a certain gain of our controller and a certain integral parameter. Of course, this schematic doesn't work, is not there, does not integrate the derivative parameter, does not include the derivative parameter, just the integral. So if this is the response we have for this controller gain and this integral term, okay, if we double the gain, we should get a response that looks like that. So it would become a little bit more oscillatory, a bigger overshoot, but should stabilize quickly. If we divide the gain, then we will cut the overshoot, but as you can see, the increase will be slower. Well, and yeah, the increase should be slower here on the term. On the opposite, if we play with the I parameter, start leaving the gain the same. So leaving the gain the same and dividing, multiplying by 2 the TI parameter, so decreasing the impact of the TI parameter by 2, you can see that it will respond slower. While if we increase the integral, if we divide by 2 the integral parameter, which will increase its impact on the equation, then we will have a faster response with more oscillation. So as you can see, we have the choice of playing with KC or TI, depending on what we want to achieve. And this comes with practice, basically finding which one needs to be corrected at a specific point. So let's now switch to our simulator and try this trial and error method. So I launch my LVProSim here in simulator mode. And I will open up a pre-configured file. Okay, apparently it didn't work, so I will restart the simulator. Sometimes you realize that you have to restart the simulator because it doesn't seem to respond properly, so just restart it. Okay, I might need to kill it completely then.
Okay.
Yes. Yes.
Yeah, I get your parameters if you need them.
Yes, we can do that also, but oftentimes I find that if it doesn't load up the parameters, it's not responding at all neither. So just checking if I can get that properly here. And otherwise I will feed it its parameters. Yeah, apparently we will have to do that.
Yep.
So in fact,
So you have...
well, in fact, I have them here, Gonzalo, okay. I think. Where is it?
CAT 0.
CAT 0, yeah, there it is.
1.005.
So 4.1005. And 1.5. So these are the values we have predetermined for this process to respond as we expect. And then I will just start my trying. That's it. It's not responding. That's what I thought.
Maybe you have to close even the Internet, the Explorer.
Yeah.
Yeah.
I'll try that.
I love Bill Gates.
Let me try again with this file because it's really convenient when we can get the meters and everything pre-configured. I think I will have a problem
Try
here.
with Explorer.
Let me close everything. Yeah, I can try with Explorer. Do you typically get better results with Internet Explorer, Gonzalo, or?
Depends on which computer I am. Sometimes it's Explorer, sometimes it's Google Chrome. So that's why I want a Bill Gates doll for Christmas. So I can hang it upside down.
Okay, so it doesn't seem to work at all. Sorry about that. I cannot launch it from there, so I need to change my.
Exactly, you can copy that address and paste it in.
That's what I will do. Internet Explorer. It's responding so fast.
Windows. You need to wear seat belts.
Oh
Meanwhile, any questions
Any?
about the process control, about the software?
Anybody? No questions up to now?
No, no questions yet.
Sorry, Internet Explorer is not responding at all. Ah, okay, finally. Let's try that. My God, it's slow. It's crazy how the computer is behaving really slow. Better and better.
Yep.
Okay, here I have my meters. We are getting there. Sorry about that, people. So sometimes, as you can see, but I don't have the parameters. Okay, so I will just input them again. So 4, 1.005 and 1.5. Okay. So now if I start my trend recorder here, yeah, good. So I'll just let that stabilize like that. So as I told you, for the trial and error method, we will just start with a low value of for the gain, in fact, a 1 typically, and double it each time to see how the system responds. So I start with 1 here. I will change my set point to 60 and see how the system responds to that. Try to go quickly with the time we have lost. So as you can see here, again, we have the 3 curves. In blue is the set point that I have changed to 60. In green, it's the controller output, so it's the pump speed in this case. And in red, it's my control variable, my level here. So as you can see, the level does not, the red curve does not reach the set point because we are in proportional only mode. So this is the error I was talking to you, the constant error, the offset I was talking to you about earlier. And we can see that the red curve did not rise high enough. We would like it to rise quickly and then oscillate at least once to get a proper response. So let's decrease, well, I will go back to 50 here. Also know that when you do a step change, it's better if you always do it in the same direction when you test a specific parameter. Like right now, I decrease my set point from 60 to 50, while before I had increased it from 50 to 60. So you should always test the value of a parameter with the same condition. So here I want to, with the value 2, I want to increase again from 50 to 60 and see how the system responds with the new gain that we have now. So as you can see, it has increased faster, but we are still far from being oscillatory. So I will go back to 50 here. And increase my gain to 4, double it, step change from 50 to 60, apply. Aha, now as you can see, we get an overshoot, we get 1 oscillation, a bit more of an oscillation. So in fact, we could consider that 4 is not too bad, but since we have 2 or 3 oscillations, probably our gain is a bit too high. So let's set it back to 3, which is the intermediate value between 2 and 4. Okay, like this. So now we would start playing with the integral parameter. So as you can see in the interface here, you have to click on this checkbox here to insert the integral parameter in the equation. So first I will start with a large, well, I should start with a large value of the integral parameter. I know to have done the experiment before that 2.4 is the proper value. So let me start with something that is not that high, like 8, for example. Okay, insert it here. And now you will see that immediately as I insert it, we start correcting the offset that we had between the level and the set point. And now I will change that back to 50 here and apply. Okay, I will set it again from 50 to 60. I will just do it one last time because you will have understood the working principle, because we don't have time to do it all, but that's the way basically by trial and error we can find proper parameters. So we can see here that our integral parameter could be more aggressive. Okay, so we can decrease it to 4, do another change to 50 and apply. And we will see that as we decrease the value of the integral parameter, we increase its impact on the reaction. So the slope becomes steeper and we correct really faster. So we can see here that at 4, I already start to have something that is not too bad. Eventually, I will reach the value that I was looking for. We found 2.4 before, which is the right proper value. And same thing with the derivative parameter. We would start with a low value, 0.1, double it to 0.2, then to 0.4. At 0.4, it will become too strong an impact. So in fact, let me show you here. Sorry, I will insert my derivative parameter and apply that. So you will see now that with the integral, proportional, integral, and derivative parameter, we achieve really, really nice control, really fast, converging really fast to the set point value with just one overshoot, no oscillation. That's the best control we can have. If I was to increase this parameter here to, let's say, 0.6, double it, okay? So you see the impact of a too high derivative parameter, and bring that back to 50 here. You see that the response of the controller becomes really erratic. When the derivative parameter becomes too high, you can see that the signals we are sending to the pump can become really erratic, and this can be really tiring for the pump, because it will receive signals that tells it to speed up and slow down. So you will hear the pump doing. So this can be really have a negative impact on the pump on the long term. So you don't want to have too high a derivative parameter for this reason. So this is the trial and error method and how to find our PI and D parameters using it. Any questions about that, Gonzalo, before we switch to ultimate cycle?
No, we don't have questions. Nothing in the chat, nothing in the questions. Perfectly clear.
Perfect.
We can go to the next part.
So let's go to the next part. So in fact, I said ultimate cycle, but I will first go to Zigglers nickels. And for that, I will go back to the example we did together last week. So if you attended the previous webinar on process control, you saw this process that I am opening now, that for which we had determined the 3 characteristics. So if you remember well, we were able, by submitting our process to a step change, and analyzing the output curve, we were able to determine the time constant of 10 seconds for the system, the gain of 0.57, and the dead time of 2.8. So these are the exact values that we have found together last week. So we will now use these parameters in the Ziegler-Nichols equations to find the proper values for P, I, and D. And this is given in the PowerPoint here. So let me go to my PID. So this is ultimate cycle here. So these are the way to get the KC, basically TI and TD parameters with the Ziegler-Nichols method. So first of all, from the three parameters I just showed you, the response time, the dead time, and the gain of the process, we will be able to derive an intermediate parameter, which is kappa here. Kappa will be used to determine the other three parameters. So if we want only proportional control, our controller gain will be equal to kappa, okay, to this parameter. If we want to have PI parameter, we will multiply kappa by 0.9, and we will multiply the dead time by 3.33 to get our TI parameter. And finally, if we want PID control, you can see the values that need to be set here. So I will go for PI control with our current setup. So we want first to calculate kappa, and we will find that it is equal to, I go quickly because, well, in fact, no, I have it here. In fact, I did some changes I shouldn't have, but I did some changes to the value. So I used in my equations, I have used a value of 2.2 instead of 2.8 for the dead time. Okay, and this has yield a kappa value of 7.97. Okay, so 7.97. If I multiply 7.97 by 0.9 because I want PI control. So 7.97 is the value for kappa. I multiply it by 0.9 to get my controller gain, and this yields 7.173. So this is the value I will input here, 7.173. But let me first check if my system is still responding here.
Yep.
Yeah, good. So 7.173, and for my I parameter, which is we said from the PowerPoint 3.33 times the dead time, which is 2.2, it yields a value of 7.326 for the integral parameter. Just all calculated from the initial values. Good. I changed my set point to 35 and apply that to see how the system responds. Yeah, that's what I thought. It's not responding.
The simulation. Click on the simulation.
The parameters would be 0. No, they're not.
Apply settings.
Apply settings.
Yep. Now it should work.
Oh, yeah, you're right. Okay. So it was not reading the parameters from the simulation. Good. So as you can see here, yeah, we will have to restart that. But again, we have changed our set point. So let's say that the set point was changed here when we applied the simulator parameters. At that point, we had our controller responding by decreasing the output to 0, and the level here increasing really quickly. So you can see that we are actually getting to the set point really quickly. Let me do another change here back to 25 with these P and I parameters. And you see that we have really a good control. So not too much of an overshoot, just one oscillation, and then we get to the set point. Finally, of course, we could add the D parameter. So I will quickly input the values that I have calculated again using these three equations here. So 1.2 kappa, 2 times the dead time, and 0.5 times the dead time to get the parameters here, which yields 9.564 here. 4.4 for the integral, and 1.1 for the derivative. $35. I apply the derivative parameter and apply here. So you will see that with these parameters, we get a really nice control, really quick, so no overshoot in this case. We get almost no overshoot and directly zooming in on the set point with no oscillation. So really fast response. So again, this was achieved simply by taking our three characteristics here and plugging them in the Ziegler-Nichols equations here. So that's a second way of achieving or finding the PID control. The last one is with the ultimate cycle method. Well, it's not the last one. Not the last one. There are other methods, but these are the three most common. So tuning with the ultimate cycle method is simply the way we will achieve that is that we will start with our process with only the proportional parameter in the equation. So no integral, no derivative, okay, just proportional. And we will do just like we were doing with the trial and error. We will start with a low value of the gain and multiply it by 2, multiply it by 2, multiply it by 2. But we will do that until, instead of having until we have a proper response and before oscillation. In fact, we will keep multiplying our gain until we get into full oscillation. So that's the goal of the ultimate cycle. We will keep increasing our controller gain until we get in stable oscillation. So what we want. So this is not enough. We don't have enough gain because we have oscillation, but the oscillation decreases over time. This is too much gain because we have an oscillation and the oscillation increases over time. So what we want to achieve is steady oscillation. So we will find the value of the controller gain that will yield a steady oscillation like that. When we have that, well, we need to know the value of the controller gain, of course, and we need to know the period of one oscillation. So typically, I would suggest that you measure it on multiple periods. It will give you a more precise result and divide it by the number of periods. But basically, we want the period of one oscillation, and using this value, which is the ultimate period and the ultimate gain that we have found on our that we have set our controller to get the steady oscillation, we will be able to get the parameters like that. So the proportional term, the controller gain will be set to half of the ultimate gain, which gives steady oscillation. For PI, it will be 0.45, and TI will be our ultimate period divided by 1.2. With the D parameter, our ultimate period divided by 2 also, and TD will be ultimate period divided by 4. Simply, we use these equations, and they will yield, again, proper control. So, for example, if we were to do it, I'm concluding with that really quickly. If we were to do it with this, again, the same setup, the same process that we just did for our Ziegler-Nichols, I will quickly tell you that we found that the proportional gain that will yield steady oscillation is 15.6. Okay, so I input 15.6 here. I put 25 here to do a step change, and I apply that, and you will see how the system starts responding with this value. So you will see that we get into oscillation. And when I speak of oscillation, I'm not speaking of the oscillation of the green curve, which is the controller output. We are talking of the oscillation of our controlled variable, the level, the red curve. How can we determine if we are in steady state? Well, it's really easy with the Y cursor. We just turn them on here, bring them to the crest of these oscillation, and then Y1 on the negative crest. And we can see that indeed on each period, we keep touching these two cursors, so we are really in steady oscillation. So with this value of 15.6, I can stop that now. I can come and read the ultimate period with my X cursors. So as I was telling you, so I set it here at my X cursor at the point where my red curve crosses the set point here, the blue curve. Okay, so this is the beginning of my period. And to get a better, well, we can make it this way here. So I get on the next period where this goes across my set point here, like that. So you can see I am at the same point one period later. And this yields 7.069 and 6.943 for a period. I can tell you if we do this minus this multiplied by 60 to get it in seconds, it yields an ultimate period of 7.5 seconds. So with this 7.5 seconds and the gain of 15.6, we can calculate our parameters. So for example, if I want PI control, again, I go back to here. So for PI control, I will multiply my 15.6 by 0.45. And for my TI parameter, I will divide my 7.5 second of ultimate period by 1.2. So in this case, it will yield 7.02 for the proportional parameter. So this multiplied by 45.45 will yield 7.02. And for the integral parameter, I get 6.25. Perfect. Turn that on. I change my set point here to 35. And see how the system responds to that by starting the trend recorder again. So you will see that these values that we got yet with another method, the ultimate cycle method, we are achieving really good control also again with one overshoot, two overshoots, one cycle of oscillation, and bang. So again, different methods to achieve the same results. Be aware though that the ultimate cycle method is not meant to be used with all systems because some systems will respond really badly to a constant oscillation like that. It could break the system. So this can only be used with systems that can stand a constant oscillation like that. Otherwise, we can try our trial and error method or our Ziegler-Nichols, which all yields a good result. And of course, all these methods yields initial values for these parameters, something that gives a result that is usable. But then the art, this is where the art comes in, the art of process control. A skilled controller operator will be able to fine-tune these starting values to achieve really perfect control on the system. Any questions, Gonzalo, before we conclude this webinar?
Yes, just one that we just arrived. Okay, it's just a comment. Yep. Very interesting presentation of your PID control. I use such algorithm as a comparison base with my artificial intelligence technique control. Best wishes for you guys from my side. Thanks so much.
Thank you. Yes, so yes, indeed, this is also becoming more and more. Of course, someday we will laugh at these really archaic methods of finding the proper parameters for PI and D control, because artificial intelligence is really coming a big way in that sense. Nowadays, we are using that more and more to get a proper result. It is faster. It doesn't need any human input, and it will adapt to new situations, which sometimes our PI and D parameters, fixed values, will not be able to respond to because it was not suspected that this could happen, but the artificial intelligence will be able to respond to that. So Thanks again for participating to this webinar. Hopefully it was useful to you. Sorry for the little technical glitch, but in fact, I'm also happy that it happened because it makes you aware that this might happen to you also using LVProSim. Sometimes it seems to be not responding anymore, so you just need to shut it down, restart, and if just doing that doesn't work, shut down your browser, restart, and then normally it should work fine. So thank you again for your help, Gonzalo, this morning.
My pleasure. Thanks so much.
Today. And see you later next week on a completely different topic. Next week, we will be speaking about transmission lines and SVC, so smart grid technologies to control transmission lines. Thank you and have a good week. Bye-bye.
Thanks so much. Bye-bye.